Vabbè, e lo schermo è questo, quindi dai, se faccio così dovrebbe andare.
Usiamo questo.
Sì,
Però
il
microfono
chiuso.
è più comodo, però non si sente poi lo stream. Però tra l'altro non c'è neanche cosa da agganciare.
Ma questo qui, dai, secondo me va bene.
Tu
Intanto stiamo qua.
hai il microfono acceso qua?
Forse sì.
Sì, penso di sì.
Perché sennò...
No, deve essere acceso qua. Togli l'audio però da qua.
Dai, penso che sia acceso. Piova, piova.
Sì, si sente, sì.
Tanto adesso la gente si sta sentendo
Bisogna
cosa stiamo
stare
facendo. Siamo in diretta.
Siamo in diretta. E questo è acceso? Come cavolo si accende?
Quando i tempi che poi la sprizza si sgasa.
Speriamo, sì.
Prova. Si sente.
È acceso, scusa?
Prova. Sì, è un po' basso forse.
Ok, acceso.
Un po' basso. Sta andando.
Aspetta che ti presento.
Sì.
Hello, so we are starting. Welcome to the AI seminars, and so we're going to have a double feature today as well. I'm Nicola Cesabianchi, a co-coordinator of the Spoke for the Fair project across the street. We're in the Department of Computer Science. And the first speaker tonight will be Alberto Marchesi, who is an assistant professor here and got his PhD also at Politecnico with Nicola Gatti. And he will talk about online Bayesian persuasion.
Okay. Thank you, Nicola, for introducing me. So in this talk, we'll talk about online Bayesian persuasion. And in particular, I will talk about a specific paper that we recently published in ICML 2023, that is the one listed here. So many of you maybe don't know what is Bayesian persuasion. Bayesian persuasion, okay. Bayesian persuasion is like an economic model that has been largely studied in economics. And at its core is a problem of how to strategically disclose information. So how can we understand the model? Like, consider this a simple example in which you have like two agents, two players. One is a seller and the other is a buyer. And the seller wants to sell some perishable item to the buyer. And let's say that the seller has some information about the item that the buyer doesn't have. For instance, he knows the quality of the item. And let's say that the item can be either of low quality or high quality. Let's say with probability 2/3 and 1/3. The question is how the seller can strategically disclose information in order to increase revenue. For the sake of the example, consider that the buyer can either buy or not buy the item, of course, and the utility of the seller is always 1 if the buyer buys, while it is always 0 if the buyer doesn't buy. And instead, the buyer gets a utility -1 if he buys when the quality is low, while it gets utility +1 if he buys when the quality is high. It's like a simple example. So it is easy to see that if there is no information disclosure, then basically the buyer, in this simple example, will never buy the item, and the seller utility will be 0. Why? Because like the expected utility of the buyer when buying the item, since the probability of the item being low quality is bigger than the item being high quality, is always negative, and so the buyer will be better off buying the item with a utility of 0, not buying the item, sorry, with a utility 0. So how can the seller exploit information? Now let's assume that the seller has information about the actual quality of the item, and how can the seller exploit this information? And Bayesian persuasion gives a way to exploit such information by committing to a signal scheme. So what happens is that the seller commits to a signal scheme for the buyer. A signal scheme is basically a machine that says that sends signals to the buyer depending on the state of the item. In this case, low quality or high quality. So in this example, let's say that the seller has two signals. Either, let's say, a good signal, that is the one on top, and a bad signal, that is to say, like, the item is good or bad. And let's say that the seller announces that he will send let's say, if the quality is low, he will send both signals with probability 1/2, while if the quality is high, then the signals will always be the positive signal with probability 1. What happens in this case? Okay, now let's say that the seller sends the positive signal, the good signal to the buyer. And what happens is that now the buyer can infer a probability distribution over the actual quality of the item by computing a posterior. So let's say here the quality of the probability of the item being low quality is 2/3 times 1/2. That is the probability that the signal sent is the positive signal and the quality is low, over the probability of getting the positive signal, that is 2/3 times 1/2 plus 1/3 times 1. And if you do the computation, you get 1/2, and with a similar computation, you get that the probability of the item being high quality, having received the signal, the positive signal, is 1/2 as well. So now, since the signaling of the seller has shifted the belief of the buyer about the quality of the item, and now the buyer knows that the item can be either low quality or high quality with the same probability. So now if you compute the expected utility of the buyer in this simple example in buying the item, the expected utility will be 0. Let's say that in such case, we bracketize in favor of buying the item, and the buyer will always buy in this case. If instead, so in this case, the decision of the buyer will be to buy. If in the other case, the signal that has been sent is the negative signal, then of course, in this case, the buyer knows that for sure the quality must be low, because the negative signal is never sent if the quality is high. And so also in this case, the buyer will never buy. But what happens is that if you compute then the seller expected utility, now the buyer buys sometimes. And in particular, the buyer buys with probability 2/3 that gives to the seller an expected utility of 2/3 that is much bigger than 0 than what the seller was getting by committing without committing to any signal scheme. Okay. So this is a simple example that explains the Bayesian persuasion model. Then, like more formally, in general, Bayesian persuasion is a game between a sender and, in principle, multiple receivers. In the example, the sender was the seller, and there was only one receiver, that was the buyer. Each receiver R has a set of actions. In the example, the action of the receiver were the other buyer not to buy. And then there is a final set of state of natures. In the example, the state of nature was the quality of the item, either low or high. So the state of nature encodes the private information of the sender. And then there is the state of nature that is drawn according to a commonly known prior distribution. In the example, it was 2/3 or 1/3. And then you have a utility function for the sender that depends on the state of nature theta, and in general, when you have more receivers, on the actions of all the receivers. And then each receiver R has a utility function that depends on the state of nature as well, and on the action of the receiver. So these are the components of the formal model. And then you have an interaction. The interaction is the one that I'm describing in the example. So on one side, you have the sender, and on the other side, in general, you have n receivers. And the first step is that the sender commits to a signal scheme that we call phi. The signal scheme is a function that maps for each possible state of nature probability distribution over signals. So in the example was if the state of nature is high quality for the item, then the probability is 1/2 for the two signals. And we denote with S here the set of signals profiles because you have a signal for each receiver R, so you have a tuple of signals in general. Then what happens is that after committing to the signal scheme, the sender observes the actual state of nature theta that is drawn according to the prior mu. Then each receiver R is privately communicated a signal as R that is drawn according to the signal scheme, depending on the state of nature theta. And then you have, as in the example, that each receiver computes a posterior probability distribution on the on the possible state of natures. And then each receiver will play an action that is a best response action, that is an action maximizing the utility. So this is the interaction, and of course the sender goal is to commit to a signal scheme that maximizes expected utility. So this formal model has been widely studied in economics, but it relies on some stringent assumptions. One of them is that the sender has perfect knowledge about receiver's utility functions. But of course, this in practice is rather unreasonable that the sender perfectly knows the utility function of the receiver. So what we do in this in the paper that I'm going to present now is to cast the Bayesian persuasion problem into an online learning framework in order to try to relax this assumption and consider the case in which the sender is uncertain about the receiver's utilities. So we do that by introducing a concept of type for the receiver. So now each receiver has a type that is taken from some finite set, and the type of the receiver determines the utility function of the receiver. Then, of course, the sender does not know the actual receiver type, and also we don't make an assumption on how the receiver types are selected. Instead, what we do is you frame the interaction between the sender and the receivers as a repeated interaction, as in classical online learning, in which the sender and the receivers interact over time. And at each time t, there is a classical Bayesian persuasion interaction in which the sender first commits to a signal scheme, let us call it phi t at time t. And then there is an oblivious adversary that selects a type for each receiver R. So let's say that the type of selected for receiver R is KRT at time t. This results in a type profile KT that is a tuple of types, one for each receiver. These types are selected by the adversary, and then the sender observes as a feedback the expected utility of the signal scheme is selected at time t, phi t, given that the type profiles of the receivers is KT. And notice that it is a problem with partial feedback because the sender basically doesn't know the actual type of the receivers, and so it cannot compute the utility that it could have got by committing to another signal scheme. And the interaction goes on for t rounds. Then, in this new model, the goal of the sender becomes that of committing to a sequence of signal schemes, Vt, to be used at each round, that minimizes the regret. So here we have some problem with the graphics, maybe when we move the presentation, but the regret is basically the difference between the expected utility of the sender when it commits to the best possible signal scheme over all the t rounds, best possible in insight, that is the quantity that you have on the left, minus the actual expected utility achieved by the sender by committing to the signal scheme phi t. And we want to minimize this regret for any possible sequence of receiver types that can be selected by the adversary. So in this way, the performance of the sender can be robust against any possible sequence of receivers he may face. Okay, so more formally, the objective is to design an algorithm that picks these signal schemes phi t, such that the regret grows sublinearly in the number of rounds t, and also depends polynomially on the parameters that define the size of the problem instance, like the number of actions of the receivers, the number of state of natures, and so on. And then we also want an efficient algorithm, that is an algorithm that has per round running time that is polynomial in these parameters. Unfortunately, as we shown in a previous paper in NeurIPS 2020, achieving both the two goals that were in the previous slide is not possible, because there is this impossibility result that says that even in online Bayesian persuasion settings with only a single receiver, there is no algorithm that can provide polynomial per round running time at the same time of sublinear regret, and at the same time sublinear regret. The question is, okay, if we require both the goals, we cannot do anything, but what can we do if you want to design sublinear regret algorithms by dropping the per round running time of the algorithm? And in the rest of the presentation, I will focus on this question. Then, if you look at the paper, we also have a part that is focused on the study other perspective, achieving the per round polynomial running time. But for this presentation, I will focus only on this aspect. Deriving sublinear regret algorithms for this setting raises some challenges that are not present in standard online learning settings. Well, because the fact that the receivers are playing a best responses to the decision of the sender, that is the signal scheme, introduces like some discontinuities in the sender utility function. And also like naive approaches that one may come up with that work by identifying a suitable subset of signal scheme, a final subset of signal scheme, and then applying online learning, classical online learning algorithms to them fail. Because basically you need to consider an exponential number, exponential in the parameters defining the problem instance, number of signal schemes. And under partial feedback, if you apply standard regret minimization algorithm, you would end up with a regret that does not scale polynomially in the parameters of the problem instance. So we need to tackle the problem from a different angle. To do that, we introduce a rather general online learning framework, and we provide an algorithm for such a framework. In such a learning framework, the key feature is that the number of possible losses that are, or utilities, if you think the other way, that the adversary may select is finite. So in general, you have like this framework in which there is a decision maker that takes decisions over time. And at each time, the decision maker takes a decision xt from, let's say, a set x. And then the adversary selects an index, dt, that is an index identifying a loss function. And then the decision maker incurs in a loss, that is LDT of xt, where LD is the loss function indexed by dt. So basically, you have a finite set of loss functions indexed by some integers, let's say, and the adversary can only select among this finite set of loss functions. And the usual performance metric is the regret, that is, as in the case that I showed you before. This case is the opposite because you have losses, is the expected expected loss incurred by the algorithm minus the loss of the best possible decision in insight. Okay, in order to come up with an algorithm for this setting that then we can instantiate in online Bayesian persuasion in order to get suitable guarantees, we like frame this problem from a different perspective by casting it in a different way, let's say. And to do that, we introduce like this vector value function that we denoted nu, that is a mapping that maps each decision x to d-dimensional vectors, where d here, I forgot to say, is the number of possible losses, the finite number of losses, such that nu of a decision x is like a vector whose components are the values of all the loss functions for the decisions, for the decision x. Then it is easy to see that you can express, you can cast the problem as a problem with linear losses, which is defined over a different decision space, that is the image of the set x through the mapping nu, and in which like you can express the loss LD of x for decision x as nu x transpose for times it is one vector 1D that is basically a vector of all 0 except for the D component, the one corresponding to the D loss that is equal to 1. What you can do now is that now you apply a regret minimizer to this new problem with linear losses. And with that, you easily get the algorithm that you have here on the right, that is, as you will see, a regret minimizer for the original learning problem. Basically, you instantiate the regret minimizer over, in general, the convex sal of nu of x, because nu of x may not be convex, but is a technical detail. But then at each round t, you ask the regret minimizer R for a decision. It will give an element in the convex sal. And then, you reconstruct a decision for the original decision space X, but first decomposing the element Z of T of the convex sal using Carathéodory theorem. And then this gives you also a probability distribution over vertices of this convex sal. And then what you do is you draw one of these vertices and you basically play a decision xt such that nu of xt is equal to z of the z that you chose by basically applying the inverse of the mapping. And then you incur in the loss LDT of xt and you feed this loss to the regret minimizer. And with this reduction, we are able to show if x is a polytope and nu is a linear map, then you can implement these procedures that I described abstractly here, that is the Carathéodory procedure and the inverse map that you need to get an x from a z. And then there exists also classical regret minimizer R that can be instantiated on the convex sal of nu of x that gives you this regret bound, that is a regret that grows as square root of T log T times D, that is the number of, from a polynomial of D, that is the number of possible losses.
Find the D plus 1 efficiently?
Sorry?
Can you find the D plus 1 points efficiently?
If X is a small polytope, the size of the representation of X, of X, if X is a polytope and the size of the representation is small, you can do.
The time of polynomial in the size of the representation of the point.
Yeah. So that is, in this case, you see, in the size D and M was the dimension of the original space. Okay. Any other questions so far? With this, now what it remains to show is how can we instantiate how to instantiate this framework in underlying Bayesian persuasion setting. First, we need to identify a suitable set of signal schemes. And there is this result that is well known in economics that you can focus on, this is called revelation principle, that you can focus on signal schemes that are direct and persuasive. What does it mean that a signal scheme is direct? Is that signals correspond to action recommendation for the receiver. So in this case, in which you have a receiver with different types, a signal corresponds to an action recommendation for each possible type of the receiver, because of course you don't know the type and you have to specify a recommendation for each type. And then persuasiveness, what does it mean? It means that the receiver is currently incentivized to follow the recommendation, so to play a recommended action. And you can enforce these with linear constraints, like here, in which basically you have that the expected utility in following the recommendations must be greater than or equal to the expected utility of the receiver by playing an action A for any possible action A. With this, basically, you can characterize the set of signal schemes of phi that are of interest in terms of a polytope P. And then also the sender's utility, US of phi k for a given k, is linear in phi. With this, the instantiation of the framework, general framework that I described before to the online Bayesian persuasion is rather simple. For instance, in the single receiver case, you instantiate the linear map nu as follows. The map maps, the set of decisions is the set of signal schemes P, and nu maps a signal scheme to a vector in Rm, where M is the number of receiver types. So here you have only one receiver for simplicity, with M different types. And the map basically takes a signal scheme phi and outputs a vector that contains the utilities for the sender for that signal scheme for each possible type. Is K1 is type of receiver 1. You have only one receiver. Minus because the framework works with the losses, but okay. And with that, you apply the theorem that we proved for the general framework, and you get that the single receiver online Bayesian persuasion with partial feedback admits an algorithm that has this regret, where the number of possible losses here is M, is intuitive, like you may face at most M different receiver and you have M different losses, times square root of T log T. And a similar reduction that I'm not going to the details can be applied to the multi-receiver setting in which you get a similar result. Okay? So, and what you get now is a no-regret algorithm that works for the partial feedback case in online Bayesian persuasion. Then, of course, there is a lot to do next. Like in this paper, we faced the problem of relaxing the assumption that the sender knows receiver's utility function exactly through online learning, but there are many other stringent assumptions of the classical Bayesian persuasion model studying economics. One, for instance, is the fact that the sender and the receivers both know the prior distribution mu. And we also tackled this in a subsequent paper, this, the problem of relaxing this assumption through online learning. And I'm not going to present you now, but I think some seminars, I think in July, Martino, that is a student that works with us, will present it. So that's it for my presentation, and thank you for
Thank you for being on time. Are there questions? Questions? Lower bounds?
Yeah, lower bound.
I know.
I mean, you have, I think, we don't have a specific lower bound for the setting, but I think some lower bounds that apply to the multi-banded case or other settings can be brought here. Now not. I mean, for sure with the dependence in T. If you mean the dependence in the other parameters,
Square root of T.
Square root of T is okay. The other parameters is more tricky, of course, because you should come up with lower bound that depend on the specific Bayesian persuasion problem. Yeah.
Question. Yes. I'm curious about the trade-off between the computational efficiency and the regression. Did you study the
Okay, the impossibility results basically also in the setting that is offline. So basically also the offline setting in which you know a probability distribution over receivers types is computationally hard. So, I mean, as a computational efficiency, you cannot do anything. What we do in this paper, and I didn't present now for reason of time, is to you enrich the model a bit. You enrich the capability of the sender. Now, the sender commits to a menu of signal scheme and lets the receiver select which one they want based on their types. And it's quite counterintuitive, but because the model, the power of the sender becomes more powerful. But what you get is that in that setting you can actually solve the problem in polynomial time. So in that setting you can derive algorithms that are no regret and per round running time that is polynomial. Okay.
Any more questions? Okay, thank you. Okay, our next speaker is Matteo Castiglioni. Unlike Alberto, Matteo is an assistant professor here. He got his PhD here, advised by Nicola Gatti. Oh, okay, thank you.
Okay. This talk is about online bidding in repeated auctions under budget constraint. And this is based on a joint work with Andrea Celli and Christian Crowell. So this is our motivation example in which, it's the main application of auctions. We have a web platform that has to assign advertisement slots to advertiser. And so we have lots of advertisers that have specific parameters like which type of user I want to target, what is the value for a click of the user, and my budget for this advertisement campaign. Then, when a user arrives on the platform, each advertiser bids to win the advertisement slot. Of course, the advertiser with the highest bid wins and then pays something to the platform. It can be its bid, like in first price auctions, or the second highest bid, like that is what happens in second price auctions. Since there are lots of auctions every second, it's different for a company to manage all these auctions by itself. So a platform usually gives you some tools to simplify the interaction. In this case, for instance, it's a real-world example in which the platform asks you to report a daily budget for the advertisement campaign, and a value for a click, a video views, or when the user see your advertisement. Then, since I'm the platform and I have only these parameters from the advertiser, I need to implement a bidding strategy on behalf of the advertiser. So here, the goal is to design a proxy bidder that bids on behalf of the advertiser. This bidder receives in input the constraints of the advertiser, so in this case, the budget, the value per click, and which type of user I'm targeting. Then, whenever a new user arrives on the platform, the proxy bidder receives the information about the user, bids, and receives feedback, the payment, and the allocation. And then of course, this goes on for every other user, and then at the end reports an aggregate feedback to the advertiser. The goal in designing these proxy bidders are, first of all, the proxy bidder must make the interests of the advertiser. So we want that it bids, incentivize the advertiser to use this proxy bidder. And then we may have other interesting properties like this good social welfare, a good revenue for the platform, and so on. So here we talk about designing budget pacing mechanisms, and of course the first properties that these mechanisms must achieve is that the total payment do not exceed the budget. And there is a naive way to do that. I bid as if there were no budget until the budget finished. At this point, I stop participating to the auction. Of course, this idea is suboptimal. Let's say that I'm seeing these auctions, okay? So the blue dots are the price of the various, okay, so in this case we can think the second highest bid that I'm seeing at various time of the day, and my valuation is $5 for every click. So one thing that I can do is to bid truthfully. So I bid my valuation $5. I win all the first slots, advertisement slots, but then I finish my budget and I stop bidding. Okay, so in this case, I do not participate to the last auctions, and of course, if I bid a smaller amount, I do not deplete my budget, and I win the last auctions that have a smaller price. So overall, my utility is largest. So we need to find other way to take more actively budget into account. A second option is probabilistic pacing. So here the idea is that I bid only with a probability at each round. But this has the problem to bid too high, so I win impressions that are too expensive. So the option, another option, that is the one that we will continue to use in this talk, is multiplicative pacing. So the idea is that I'm scaling my bid by a multiplicative factor. And in this way, as you can see, you take all the bids, you win all the auctions that have a small price. And in this way, I can finish the budget at the end of the time. So, okay, in this talk we will talk about multiplicative pacing, and formally we want to find this parameter alpha that may change between one round and the other that scales the bid, the valuation. As a first setting, we will see repeated second price auctions. And second price auctions are easier because when you don't have budget constraints, the best thing to do is to bid truthfully. So if my valuation is $5, I will bid $5, and this is optimal for me. This is not true in auctions with budgets, but this property will be useful in any case. So this is the formal framework. We have a sequence of capital T rounds. At each round, the bidder observes a valuation VT, then submits a bid XT, and observe a reward function FT of X, that is the difference between the valuation and the second highest bid. If my value is greater than the second highest bid and zero otherwise, and my cost is the second highest bid if I have the largest bid. The bidder knows the horizon T, capital T, and we will denote the per iteration budget rho equal to the budget over capital T. We are in an online setting, so we assume that the bidder knows the histories. and the current valuation, but has no information about the future inputs. This setting has been studied by Balsier and Gore and show how to pace the spend using a single dual Lagrange multipliers and controlling these Lagrange multiplier through a subgradient descent scheme. So this is their algorithm. We have a Lagrange multiplier mu, and at each time I observe my valuation and construct a paced bid. That is my valuation scaled by a factor 1 over 1 over 1 over 1 plus mu t if I have enough budget. Otherwise, I bid all my budgets or my budget. Then I observe my spend and I update the multiplier and the available budget. So the idea is that if I spend too much, so the cost is higher than the raw budget per round, then the multiplier will increase, and so in the next rounds my bid will be smaller. Why? If I'm spending too little, so C is smaller than rho, then the Lagrange multiplier decreases and my bid will increase. Now the results, as a baseline, they take the reward of the best dynamic and feasible sequence of bids when the input sequence is known in advance. So this is the optimal allocation under full information. And they show that the algorithm achieves a raw fraction of the optimal utility plus a sublinear regret term. Okay, and this result holds in any setting. So, for instance, when the F and C are adversarial. If we are in the simpler setting in which the inputs are sampled from an unknown underlying distribution equal in each round, then the algorithm suffers only sublinear regret with respect to opt.
Sorry, Matteo.
Yeah.
You're scaling the revenue of the player by role,
Yeah.
which is like alpha regret because
Yes, it's equivalent to alpha regret, but in this literature you use competitive ratio that is like the opposite of alpha regret. Yeah.
you're scaling up the revenue of the player in order to be able to
Yeah.
pay them off against them.
Yeah. And rho is essentially the parameter of the alpha regret, your alpha.
How big is that problem?
This rho is the budget per round, so budget over T. So if your budget is high, your performance are good. If your budget is small, your performance are not so good. This is the idea. Any other question? Okay. So now our contribution to this field. So how can we adaptively pace bids in repeated non-truthful auctions like first price auctions? Okay, because here it's not sufficient to scale the Lagrange scale the bid because the auction is not truthful, so you have to bid more strategically. And we study a general framework that generalize both our bidding problem and the adversarial bandwidth knapsack framework. And we consider capital T rounds interaction in which there are M budget resources, so not only one, not only money. And at each round, you pick a decision xt from a set X, and then you observe a reward function F and a cost function C. And the goal is to maximize the reward subject to the budget constraint. We assume that there is a void action, so an action with cost 0. In the auction setting, this action is essentially bid 0, okay? And we assume that the per round budget is constant, so capital B is linear in T. We provide a best of both worlds algorithm that works both for the adversarial setting and the stochastic setting. In the adversarial setting, we take as input as benchmark the best fixed action in insight. And in the stochastic setting, we take the stronger baseline that is the best dynamic policy when the decision maker knows the underlying distribution, but not the realization set each round. These are our main results. We provide a constant factor competitive ratio in the adversarial case whenever the budget is linear in T. And these answer an open question from the adversarial bandwidth with the knapsack framework and improves the best lower bound of log T. Our algorithm is a best of both worlds algorithm, so works as optimal performances both in the stochastic setting and in the adversarial setting, and it requires minimal assumptions on the reward function f and the cost function c, because we only require that there exists a suitable regret minimizer for this function. And of course, we have an algorithm for our motivating applications that is budget management in repeated first price auctions. So this is our idea. We play a two-player zero-sum game between a primal player and a dual player. The primal player chooses a strategy, a mixed strategy over the decision space X, and the dual player chooses a dual Lagrangian multiplier lambda. Then, this is the game they played, so it's the Lagrangified problem. And then they observe as losses utility the result of the game. And we continue to run this game at each round. The question is how to compute this C and lambda, and we assume that there exist regret minimizers for these problems. And we regret minimizers, we mean algorithms with sublinear regret. So in the algorithm, first the players chooses the decisions, and then we update the algorithms with the losses. And here the idea is similar to the one of the previous algorithm. So if I'm spending too much, then the Lagrangian multiplier will increase, and I will start spending more, spending less. We provide a similar result to the one for second price auction in this setting. So we achieve a raw fraction of the optimal utility, suffering an additional sublinear regret there. And this ratio rho captures the relative wealthiness of the bidder. And this guarantees holds both for the full information setting and the bandit setting, because we only need a regret minimizer, a primary regret minimizer for the specific setting understand. And in this stochastic setting, we achieve sublinear regret. And that's it. Thank you. This is our paper and some literature.
Yes. Questions? Okay, let me start. So again, is this so you're showing a red bound at alpha 1 over rho.
Yeah.
So now, is there a possibility of balancing? I mean, because somehow it sounds okay. What would be? Is this 1 over rho choice of alpha like natural?
It's more than that. It's optimal. So, I mean, you always have to balance regret and competitive ratio, but you can show that this competitive ratio is optimal also if you admit like almost linear regret.
So it means that you cannot get severe regret if you have a smaller alpha.
Yeah, that's true.
And this is already for the simplest case. This was proven in the
Yeah.
more questions. Okay.
I think it's time.
You know what the script is?